Esatto, muchas gracias.
Okay. Good afternoon. So today we have the fourth presentation in this cycle of Good Neighbors, and at this time we have Dr. Juan Rey from the company Mecanismo, and the presentation will be Conceptual Design of Building Structures. Juan Rey is a civil engineer from the University of Catalonia. He taken the Ph.D. in architecture at the University Polytechnica of Madrid. He has more than 20 years of experience in the design and calculations of building structures. Since 2003, he is the director of the company Mecanismo. Since 2007, he combines his professional activity with teaching at the University Polytechnica of Madrid and also at the University of Catalonia, and also in other foreign universities in the United States and in Taiwan. About this lecture, Juan Rey will present several case studies, and the focus will be placed on the conceptual issue in the development of building structures projects. It will be shown a wide range of project situations, several projects with different materials, with different typologies, and with different scales. Dr. Juan Rey, thank you very much for accepting our invitation, and please take the floor.
Thank you. Thank you very much for the presentation, and also thank you very much for the invitation. It's my pleasure. And the title of the lecture is Conceptual Design of Building Structures, and I will try to show some examples of some projects we have developed these past years on Mecanismo. But before that, before entering in that, I would also like to focus on 5 concepts or ideas that I found interesting related to this issue of developing or designing building structures. Okay, thank you. So the first one is the boundary conditions. I found this specifically important, and I will try to explain myself. When you start a new project, there's always like the blank syndrome of not knowing what to do. So you always need like direction or some initial ideas for trying to focus on some directions or whatever. So I found boundary conditions very important in the sense of having some paths to explore in each case. And also the interesting thing is every project is different because we have different boundary conditions, different budgets, different countries, different colleagues working with you. So for instance, this is a competition we won recently in Milano, in Italy, for a new building from La Scala in Milan. And here the concept of the competition was these origami shapes for this huge steel structure. And I think this kind of ideas or this kind of boundary conditions are always really, really helpful to try to focus all people involved in the same direction. Second is the design process, to try to enjoy the design. Now we are always focusing on the final result, on the images. We are always looking images of many, many things. And I think that the process is very, very important. And I think we have to take more time for thinking things and correctly developing the ideas. So I think also this is a key thing in developing building structures. Next one, of course, is the teamwork. These are my colleagues at Mecanismo, but not only them, also the architects and the contractors, all the huge or very big teams that normally are involved in a project. I think it's also important to take this into account and to try to make the most of all of them. Also creativity. I think that we always look at civil engineering as something very technical and boring and straightforward, but I think it's also room for trying to get out of the box and to, not all the projects are meant to be like really extraordinary or design-driven projects, but some of them, yes, and I think we have to also take the opportunity to explore or to experiment different things at some projects. And finally, I like this quote, well, not a quote, this title of a film by Spike Lee, Do the Right Thing. And this is really the difficult task of which is the appropriate or the structure that is more appropriate for each specific case. In other contexts, it's easier because the optimum economically speaking is the thing you have to do. But when dealing with building structure, there are many factors that have to be taken into account. Economy, of course, is one of the most important ones, but also, for instance, interaction with MIP, with facade, clearance, appearance of the building, aesthetics. There are many factors that have to be taken into account. So every project is specific and have to be considered as such. Okay? So after this, I'm going to present 9 examples of different projects. I did a selection to try to have all materials and all scales to be as different as possible. Sorry, the first one is the renovation of a square in Teruel in Spain. This was an international competition, architectural competition, and this is the old part of the old city of Teruel. And here it was an old market. The idea was to demolish this market and to build a new building with mixed uses, very different uses. It was a multi-purpose building for having like sport facilities, like a basketball court, have a small auditorium, also a cafeteria and some offices. So many different uses on the same building. And the idea of the architects in this case was, instead of building like a new volume on top of the plaza, to build it below ground, you see, and to liberate the public space of the plaza. That sounds nice, and it's nice, but it's challenging from the engineering point of view. So this is more or less the plot we had, and these are the existing buildings here. So it's more or less 20 by 60. And of course, we have to design a diaphragm wall to make the excavation possible. But then we have to solve all these different uses, thinking, of course, in the architectural program, okay, in the spaces that have to be there. For instance, we needed a basketball court, so it will occupy most of the footprint of the building. So it was not possible to have columns there because we have the basketball court there. So the first idea that probably we all have in this situation is to try to span in this direction, the shorter span, that is 20 meters, not small, but it's the shorter span to try to solve this problem. The fact was that due to these strange volumes we had, that was not possible. We found out that it was impossible to cross with steel trusses or something similar in that direction. So we end up having, two steel trusses, but on the main direction. We placed 4 columns on around the basketball court, and we have 1 truss between the ground level and -1 level, and another truss between -1 level and -2 level, liberating this area for the basketball court, for being able to have clearance for the practice. So you can see it here, the position of the 2 main trusses that more or less follows the volumes of the program. This was the first issue we had, but the second one, the most important one, was the horizontal forces we have because of being the building below ground. And also because of the geometry, we have only one level, this intermediate level, that could be used as a path for these horizontal loads to connect from one side to the other, because this level, we don't have anything because of the basketball court, and this other level, as you see, the geometry is not very favorable for this. So at the end of the day, we had to connect all the horizontal forces through this only intermediate level, and considering also that that intermediate level have quite a lot of big openings for trying to let the light enter through the building, and also for the vertical stairs, elevators, so on. So this is one of the first calculation models we developed, and the surprise was this big amount of compression forces we had horizontally because of this issue I was mentioning. So this is the first proposal for this intermediate level. We placed some horizontal steel trusses to provide the stiffness and to make some paths for these loads to go from one side to the other. This was the first approach we had. I have to mention that during the project, we were not able to have like temporary anchors for the excavation, so we had to use this as temporary like stabilization for the structure. Then before the construction, we've been told that, okay, you can have temporary anchors, if not, it's going to be really, really complex. So we changed the design of the diaphragm wall, and we were able also to eliminate most part of these diagonals and to have a composite structure, as you are going to see in the next slides. This is the fabrication model and some of the details of the connection. The constructor was FCC in this case, and the steel manufacturer was Horta Coslada. They did a great job. And these are some pictures of the process. This is the big hole we had there with all the buildings around. And you can see these temporary anchors that finally we were able to place. And while we were doing this, the good thing of the steel structure is that you can prefabricate. So while this was being done, there was the fabrication of the steel structure. Here is a quite interesting thing that Horta Coslada suggested to build the trusses. There was over 40 meters on their facilities. Instead of building 3 pieces, that was what we were thinking, to fabricate it in one piece and then to transport it to the site. So they did that. You see the transport, the special transport of the pieces. It was quite challenging because of the access to the site. It was not the best access, and you see here some other pictures of the process. Okay, the process took 1 day of putting these 2 trusses on their position. You see here some pictures of the process. You see the connectors for the composite structures, and also bolted connections on site. All of the works on the facilities were welded, and on site all the connections were bolted. And so you see the 2 trusses at 2 different levels, as I was mentioning. And then secondary structure. You see that we have nearly no diagonals because finally we have a composite structure, so we are running the compressions through the concrete we have. But we still have some diagonals at some specific locations in which we need it. And some pictures of the final result. Here is the -2 level where we have the basketball court, and they painted all the structure in red, also with the fire protection. So you can see here the final result of these spaces, and also the final result of the plaza. Okay, so this is the first example of a steel composite structure. Second one is also still a structure, but this case is a renovation of an existing building in Madrid. This is Matadero, Madrid. That is the old slaughterhouse. It's a quite big complex of, I don't know, maybe 15 buildings, something like that. Old buildings. They were built between 1908 and 1928 by Luis Bellido, was the architect in charge. And this was abandoned on the 80s, last century, and then around 2003 or 4, something like that, it was a big project to transform this area into like a cultural hub with very different uses like library, theater, exhibition areas. So we were lucky to participate in 5 of those projects. I'm going to talk a little bit about this one, Pavilion 8 and 9. They are similar, but I'm going to focus on Pavilion 8. So this is the existing building. It's 70 by 34 and it has 4 levels. It was an old slaughterhouse, so the upper level is open, and also a funny fact is that all the floors are not horizontal. They are inclined in order, because there were dead animals there, for the blood of the animals to go through the facades of the building. So the idea was to transform this building into a, was not very clear, but something cultural, exhibition areas. So at the end of the day, we had to consider 5 kilonewtons square meter of use at all the levels. Okay. So the structure of the building, the interior of the building is a concrete structure. Pavilion number 9 was one of the first concrete structures in Madrid. This was dated 1912, if I don't remember wrong. And then we have perimeter walls made of brick and stone. Okay. You see that they are one of the first concrete structures when you see the typology. That is not a natural typology for a concrete structure. We have like many different orders. It's more like if a timber structure or a steel structure was like directly transferred into a new material, right? The columns were really, really slender, as you see, and the state of maintenance of the structure was really poor. It was abandoned for over 20 years. So when we get there, we saw like many things that were not very good. Okay, we have corrosion, and we have even problems of buckling at some points, at some columns. We did, of course, a lot of research and testing on the building, and we came up with results of the resistance of the concrete around 7-8 megapascals. And so the conclusion was that the building was not able to support 5 kilonewtons square meter. We have to strengthen the building. But before all this research, an architectural competition was launched for, say, what to do with the building. The competition, Arturo Franco won, the architect won the competition, and his idea for the building was to try to keep it as it was. His idea, okay, this building is really nice, let's try to do nothing. Just some kind of partitions with this kind of ropes, and let the building shine as it is. Okay, after the competition, we did all this research and this testing, and I had to tell Arturo, okay, this is not possible. We have to strengthen the building. This is not possible to do this. Okay, so we had to change the plans, and we started to work together on different approaches on how to strengthen the building, but to try to keep as much as possible this initial idea, this initial boundary condition we had of trying to remain as much as possible visible the existing structure. Okay, so we did some calculations and we came up with that the existing structure, if we repair all the corrosion and all things, was able to support the self-weight of the structure, okay? But not more than the self-weight. If we wanted the existing structure to support greater loads, we have to strengthen the structure, okay? So we explored many different options, and finally we came with this idea of constructing a new steel structure inside the building. It's like to build a new building inside the building. So instead of strengthening the existing structure from below with steel beams and with attaching steel profiles to the concrete ones, or even increasing the section of the existing concrete columns, we came with this idea of why not to build like new steel columns, but not attached to the existing ones, in order to be able to view the existing sections. And instead of strengthening the existing structure from below, why not to build a new level on top of the existing one that would be able to resist this additional load, this 5 kilonewtons square meters, and transfer directly all these loads through this new structure. So the existing one will only need to support itself, okay? This is like the key idea. Also, this was really good in terms of that, since we have these inclined floors, now we have new horizontal floors, and we have these spaces in between the existing and the new floors for running all the services through this space, okay? So we build new foundations. This is the process. We open like holes around the existing foundations. We build micropiles, 4 micropiles per column. We build like 2 small pile caps, concrete pile caps, and then on top of it, like a small steel pile cap. This is only because the clearance of the ground floor was really tight, so we need to adjust the height of the pile cap as much as possible. If not, a concrete pile cap would be easier. And then we provide this new steel structure. We made some holes on the slabs. You see? The idea of separating the new steel structure from the concrete was also good to avoid this interference with the existing beams. And so we continued with the columns from one level to the other. You see the columns like on the next level. And then we provide some main beams and secondary joists in the other direction. And then on top of this is going to be like a timber flooring. So at the end of the day, you are only going to see these steel columns. The other will remain visible, okay, in all the floors. So this is more or less the idea. Here would be all the services running below these new floors. And this is the ground floor with the pile caps and also the appearance of those levels. Even at the end of the project, the architect decided even to create a triple height like main entrance to the building, in which we demolished the concrete structure and only left this steel like strengthening for the building. Okay, so this is again another steel structure, but in this case inside an existing building. Okay, another steel structure. This is the Spanish pavilion for the Expo, Dubai Expo. It's just being closed a few months ago. Now it's being dismantled. It's again an international architectural competition. In this case with Amman, Cánovas, and Maruri. And these are some images from the competition. So the idea was to have like some underground levels with all the program of the exhibitions and auditorium and all the program, and then to have this plaza on top with these cones structures for bioclimatic purposes. Okay. So the main challenge from the structural point of view was that these cones like the columns of the cones, are not reaching the foundations. They stop at the plaza level, and we have to prop all these loads at this level, okay, to avoid this interference of all these columns on the underground exhibition spaces. Okay. Inside the cones, we have these domes, also for exhibiting different topics. Okay, so we have some cones, and then inside some domes, and then all the program in the underground levels. And on the competition, because the Dubai Expo was the expo for the sustainability, we suggested and we proposed to have a timber structure on the underground levels. Okay? We won the competition, but then afterwards we were asked to remove the timber structure. It was not possible to have timber structures and to construct it in steel. So we changed a little bit the concept. It was easier with the steel, I have to say, but we changed a little bit, and all the building is completely made of steel. So this is like the beam model we developed with the final, after all the final design process, the beam model of all the cofferdams for the retaining system, and all the steel structure of the cones, the domes, and all the different levels. Here you can see it, I think it's clear with the different layers, say, like the cones, the domes, like inside of the cones that are hanging from the cones. Then the plaza level, that we have to support all these loads of the cones, and then also the inferior levels. And there are a specific, very special structure on this main cone that we have like a huge ramp going down, and it was quite a special and like difficult part. We began with these numerical models for the wind loads. There was like the main, the governing load here was the wind load, of course, on the cones, and this is not a very easy geometry for, and also with this position, one after the others, and how to evaluate wind loads in these kind of structures. So we began with this kind of analysis, and then we also did wind tunnel testing for having more like accurate values for the wind loads. And another interesting thing is that all these cones, the facade of the cones, were like fabrics, like tensile structures. So it's hard to transform these pressures into tensions or compressions in different points of the steel structure, depending also on the direction of the wind. So at the end of the day, we have these models with the pressures of the wind, but we have to transform this into loads at the nodes, at the points of connections of the tensile structure and the steel structure. So this in pink, you see all these arrows, are the different forces, sometimes tensions, but not in the direction of the wind, in the direction of the reaction of the fabric. You understand? So it was quite tricky to move from the wind tunnel test to the calculation model, but well, at the end of the day, we have some forces and we designed the steel structure. And this is the geometry of this huge ramp I was mentioning, that was solved with some cantilevers, with some frames and cantilevers. Some pictures of the construction. It was all steel structure. It was also welded on the facilities of the contractor, and then all the connections on site were bolted, and big like parts of the structure were prefabricated, as you are going to see, and then bolted. We had different types of connection, depending if they were going to be visible or not, for economic reasons. And you have you see these rings. There are for auxiliary structure for the tensile facade. This is you see a lot of scaffolding. This is like the temporary auxiliary means for the construction of this ramp I was mentioning. Of course, then after we remove all the scaffoldings, and the ramp was in cantilevering. And this is one of the domes, one piece of one of the domes, and this is the final result of the building with the plaza, the cones, and these are some of the interiors of the different pieces. And this is the ramp, and with this like art installation that we also developed the engineering for the teams. It was a very interesting job, and you see the ramp and the piece of art. Okay. So let's move now to concrete structures. This is a quite old project, was 2008 or something like that, I think. It's a conference center in Spain, in Extremadura. And you see more or less the idea of the building, the idea of the competition. It was also a competition. It was to have like an underground ring here. The building was like buried, underground ring. And then this main 20 by 20 cube that had like the main auditorium. We have one main auditorium here, secondary auditorium here, and the exhibition area here. And then this is all the spaces for services. So these are some images from the panels of the competition. You see here the main stage area for the main auditorium that is below ground. And then on top of the stage, we have two levels for practice rooms and also a restaurant, cafeteria on top of the cube. And then the rest of the program is below ground. Okay? And we have on the center, like kind of plaza, the entrance of the building. I'm not going to enter into many details because it's a very big and complex project, but only to focus on some like conceptual or I think interesting ideas. I think this kind of aerial views are quite right to understand the different parts of the project. This is like the exhibition area, and here, since we have to have soil on top of it because it's all below ground, our idea was to have these inverted concrete beams just following the position of the columns. Like it seems like not very like orthogonal structure, it's not, but it's simple because it's column to column, one inverted beam, and that's it. The columns were like the arrangement came from the architecture, okay, so it was not very orthogonal, but it was okay since it was going to be with soil on top. Then we have the main auditorium, the secondary auditorium, and the space for all the installations. So the main auditorium was quite a big hall. We have water there. It was quite difficult. We have to provide a quite thick slab, rough foundation below. And we have like a big void here because of the main stage. Okay, we don't have any floors in between. You see here the secondary auditorium, and you have to see now here the main auditorium was all with composite structure, with steel beams, connected to a steel deck on top. And then I'm going to focus now on the box. Okay, here we experiment together with the architects quite a lot on the textures and colors of the concrete. Most part of the concrete structure is visible, so we spend some time at the beginning of the construction process on experimenting a little bit with colors and different textures. And at the end, the architects decided to have this color that more or less matched the color of the soil there, and also to use a lot of like different approaches with the placing timber in order to have this kind of textures. Okay, so you see here this kind of textures also on the ceilings, and you see here the final result with soil on top of these inverted beams we were seeing on the previous slide. And then the box, the main box. This was the most complicated part of the structure. We have 20 by 20 by 20 we have 3 phases in which we have like columns. Then we have the other phase, we have this stage, it's not possible to place columns, but it was quite easy since we have 20 meters high of concrete. So it's, after you have 2 or 3 meters, it will be okay to support itself. Okay. And then we have also we place 2 steel trusses in order to be able to build these 2 levels on top of the box. Okay. So some pictures. The idea was to make this. We discussed a little different approaches for the holes because they were all different geometry for the holes. At the end of the day, we decided to do it like this with laser cut of these pieces of span, and then to use like sliding formwork, sliding formwork, and also this kind of texture for the concrete, the colored concrete you see. Okay, so you see we have like a kind of box, but with nothing inside because we have the main stage of the auditorium. Okay, and then on top we have these steel trusses with 2 levels on top. Okay, these trusses also are needed for this stage, for moving all the things of the stage, so they have this double use. And this is the appearance of the box once it was the concrete part finished, and then on top of this it has the facade. It's like a steel substructure with some ropes, like having like the exterior dress of the building, something like this. It's like a steel substructure with some hangers and these kind of ropes with this kind of interior feeling. This is like an image from inside the restaurant on top. And these are some images of the finished building on the night with all these lights. These are the lights of the main auditorium that have these skylights on top. And some other pictures of the finished project with this exhibition area and the main auditorium here. Okay. And this is an aerial view. This is a real view. No, it's not a render. This is the aerial view of the building. Okay, good. So next one, linking with this idea of concrete and also with the structural facade. This is a project we built in Kenya some years ago in Mombasa. It's a residential building here near to the creek. And the idea was to also have a structural facade, structural concrete facade, in this case with this kind of geometry, with different patterns, okay? And to be able to build this in concrete with only the internal core and this facade, try to liberate the interior space for living areas. Okay, so we have in these three phases, we have this concrete facade, concrete structure on the facade. Then we have this concrete core on the center of the building, and then we have some concrete beams and slabs for solving the floors. Okay, so these are the patterns. Really, we have like 4 or 5 small bits that are repeated. They are not all different. We have like some patterns, but it was really challenging from the constructive point of view, how to deal with all these joints, with the reinforcement. And I have to say that maybe if this project was meant to be built in Madrid, we were not able to make it happen, but there in Kenya, everyone was willing and was pushing to construct this, and at the end of the day was very successful. So we did some mock-ups to test if we are going to be able to do this. And after the mock-up, we decided the architects also decided to paint it white to avoid like having a lot of headaches with the appearance, the finishes of the concrete, just to paint it white and it's okay. And these are some pictures from the constructive process. With this You see these concrete elements. Here we use a different approach for the openings. Instead of this polyexpand, we use timber with some hinges in order to be able to reuse the pieces at some other points, since we have some patterns that were repeated. Okay, some other pictures from the constructed on the side, and then the finished works. You see the facade, the structural facade, the entrance for the cars, and then some views from the interior. I think is quite nice, the final result. Okay, now this other project is also abroad, in this case in Puerto Rico, with Pardon Ebrard Architects, and is the headquarters for an energy company. They're in Bayamón, in Puerto Rico. Here the main issue was, of course, horizontal forces. I mean, the eye goes to the cantilevers, but the main concern were not the cantilevers, were the earthquake and also the hurricanes that we had on the area. They had earthquakes nearly every day there. So we used, in this case, we used couple concrete shear walls as a main earthquake system. We had like a really big core here, another core here. The building is regular in its geometry, but not in its stiffness. That is a really big issue. But I mean, the architectural, it was mandatory in this case, and we had to deal with that, with these irregularities. We had this too, and then we have some other shear walls at some other positions to try to deal with this. Okay. Then the rest of the structure, we have steel columns, steel trusses, and precast hollow planks, because we have really big spans even in the secondary direction. If I don't remember wrong, 12 meters between the main trusses. And then we have these big cantilevers. I don't know if it was 8 or 9 meters cantilevering on the perimeter of all the levels. So these were some of the details. We have here a problem with the clearance of the floors and also with the MIP conducts. So the trusses are really not very much optimized. This, again, boundary conditions. It was not possible to have the structure we would like to have, but we have to negotiate between different areas to find something that suits all the different questions. And you see here some different images of also the constructive process. You see the main steel columns, the precast hollow planks, and you don't see the cores. The cores are inside the building, and I think it's quite nice the scheme the architect proposed, because from the outside you don't see the facades are really clean because they don't have any columns or facade. So all the structure are really inside of the building, and you have this kind of like very light appearance of the final thing. Here below this you have the concrete core here. This not attached to the facade, so I think it's quite nice. You see here the big concrete core we have in this corner, and the some final pictures of the building. But you see the facade is completely liberated from any columns. Okay, completely different thing now. Now this project is more about geotechnics. Sorry. Okay. This is a residential building in Madrid. This is now being finished almost, and it's a very straightforward building in the sense it's concrete and nothing really special. But what's the special or the interesting thing of this specific project is that at one point during the process we were asked if it was possible, because it's like 1, 2, 3, 4, like 5 or 6 levels above ground, and then we have like 4 or 5 below ground. with an automated parking. Okay, and we were asked before of the deadlines of the project if it was possible to build upside down. Okay, to build before like first we build the ground level and then we go to the different levels below ground, but extend this idea of once we have the ground level to be able to construct first floor and -1 floor at the same time and go up and down at the same time with the construction of the building. So we explored this possibility and we thought it was possible, and this is the explanation on how it is. So we have these levels above ground and these levels below ground, and the idea was to try to build all at the same time, the parking and the residential floors. So more or less the geometry of the building. So the idea was to first, of course, you have to build the diaphragm wall to retain the soils on the perimeter of the plot. And then we built some micropiles on the positions where we are going to have concrete columns. So we have now micropiles that at the end of the process are going to be concrete columns. So these micropiles are going to support, temporary support, the upper levels, and also to support the excavation, to be able to support the building while we are excavating. Okay? So this is more or less the process. We needed, of course, some temporary bracings to avoid the buckling of these micropiles. And this is some pictures of the process. So first, this diaphragm wall all around the perimeter of the buildings. Here you have there are concrete piles. These are the positions when we are going to have the columns. We changed a little bit during the constructive process, and we decided instead of starting on the ground level, starting on the -1 level. So you see, we pre-excavated one level. Just was a matter of economy to try to reduce a little bit the budget. So we started on the -1. We did these micropiles, these quite big micropiles. On this level, you see the connections for the slab we are going to pour directly on top of the soil of the -1. Okay? So you have all these connections and also all these connections for transferring the loads from concrete to the micropile. Okay? So we directly pour the concrete using the soil as a formwork, okay, on the -1. You see the columns, but below we don't have any foundation, say, we only have these micropiles connected. Okay, so the building is going up and going down at the same time. Because you see we are like constructing the different levels. They are like standard concrete slabs. Some proteins at some levels, but nothing very specific. But then this is the -1 level, and we are now excavating below at the same time, excavating under the building that is in the process of being constructed. Okay? So once we remove the soil of one level, we introduce the reinforcement, we pour the concrete, and we continue like also pouring the next slab and continuing going down. With this, the point is that they finished the upper levels, the structure of the upper levels, and it was possible to continue with the installations and with the finishes at the same time that we were finishing the structure of the parking. That is more time consuming because of the soil. Okay. So you see the process. We need some temporary bracings for stabilizing these elements. Continues to go down. And this is like the last level. You see here again the bracings because we are connecting to the pile caps. Now we do some pile caps there, and we finish the process of constructing the underground levels. Okay. Now it's more or less clear the idea. Okay, so I'm just finishing the presentation. I have 2 or 3 more examples of like small scale projects that I found it also very interesting, because normally we speak about big and challenging projects, but sometimes the smaller projects are very, very interesting because you can experiment a little bit more, and sometimes they are really challenging also in terms of the structure. This is an example of a timber structure in Galicia, in Spain. It's a viewpoint for a winery in an amazing location. And the project is really small. It's only this piece of timber structure. It's a modified, chemical modified timber structure of Acoya for durability issues. And then we have this concrete structure that provides stability to the timber structure, and some auxiliary like stairs and some other parts. This is also the fabrication model for the timber, same as in steel. You can produce like a digital model in order to fabricate directly all the joints and all the different cuts that are needed. So you see here some of the details of the structure. This kind of structure, small scale project, of course, at the end of the day, you focus more on the details because of the small scale of the project. That I think is nice also. The different joints of the pieces, and here some global views. Here, in fact, in this piece, I think I have some other pictures. This is like the Shousugi ban. This treatment you apply to the timber. You burn the timber in order to provide more durability to, in this case, to the pine pieces. This is a Japanese technique, ancient Japanese technique. It was used here as well. And some pictures of the final result of the project that I think is quite nice. Small and simple project, but I think it was a really interesting experience. And the place is amazing. I recommend you to go there and have a wine there. It's an experience. Okay. Very different thing again. This is a collaboration for an art installation. From the artist is Janet Eckelman from the USA. And this is a piece that was installed in Plaza Mayor in Madrid a few years ago. So the idea was to provide support for this net, for this tensile structure that was meant to place it on top of Plaza Mayor. Okay, was like a couple of months. So, and this is the artist Janet Eckelman, and this is the kind of things she does with this kind of elements from like ropes, nets, and this is like the piece. This piece was previously in Sydney, Dubai, LA, and a few other cities. It was like, and in most of those cases, it was like attached to existing buildings. Okay, so here we started asking if we were able to attach to the existing buildings in Plaza Mayor, because it was like the easiest way to solve this. They told us the buildings are protected. It was not possible to connect to the buildings, so we have to provide like an auxiliary temporary structure to be able to place the piece of art on position. Here below the plaza we have a parking. So this is slab, concrete slab. Okay, we don't have soil below, so we have the challenge of having these big horizontal forces because it's a membrane. Okay, so we have big horizontal forces. So for avoiding this effect, we have to have some dead loads, big dead loads. But those big dead loads, we have to take into consideration. We have a floor, so could not be so big. Or if it were so big, we have to. We needed like big areas to try to match the actual design load of the floor. These are the values of the reactions. We have like 6 tons, something like that, of reaction. It's quite high. And this is the position we chosen for placing the piece on the. And this is the kind of structure we were thinking. First, we designed like a proper steel structure, but we were advised that the budget was really low, and they suggested us to try to, since the piece was meant to be there for 2 months, to try to reuse like existing structures, like rental structures, in order to make it cheaper. So we said, okay, no problem. So at the end of the day, we use it like this kind of trusses for the stages of concerts, okay, and also like dead weights from cranes, and auxiliary elements of the construction industry, okay. So the structure is not very, sexy, if you want, but it's cheap, and I think it's okay for being there for 2 months. So you have these main vertical elements. In plan, we have these auxiliary like arms to provide the stability, and these retaining cables also for transferring the loads. The calculation of this is really simple. You don't need much calculation or calculation models for solving this. The only point was to design properly how to transfer the loads to the floor on the plant side. Okay, so this is like the net. It was like small box, but then was like providing really high values of loads of reactions. And this is the process we use, as I was mentioning, like dead weights of cranes, these auxiliary like formwork elements for providing like enough areas to spread the load on top of the slab. And this is the process of putting the piece on top. We have some load cells and some anemometers in order to try to monitor all the process. Also, not only during the construction, but also during the few months that the piece was there, because to evaluate the wind loads on this kind of a structure is really, really difficult, considering where they are placed even more. So we implemented a system to monitor all these values of the loads and be sure that they were more or less the ones we predicted on the calculation models. And also for the pre-stressing of the 4 ends, we use these load cells to apply the pre-stress little by little on all the 4 ends of the bits. And this is the final result. During the day, you see here the auxiliary elements. They are not very, but I think they are okay. And during the night, it was really beautiful with the lighting on top of the plasma. Okay, and I think this is the last example. Really, really small bit we did here, but I think also quite interesting. This is a building in Ibiza, in Spain. We did not the structural engineering of the building is not ours. We only did the consultancy for these elements, for these canopies that are built with ultra high performance concrete. They are built from concrete, these elements, okay? So we provide consultancy for these elements and the connections only. The other was made by others. So these are the pieces, the geometry of the pieces, more or less 2 by 2. And the idea was to try to build it with ultra high reinforced concrete, okay? In this case, 100 megapascals concrete. And then we have those steel elements to connect those elements to the structure of the building. So we did some testings of the material, and we have this compression resistance of 100 megapascal and this FCT of 24. That is the value that it's relevant in this case to avoid cracking in the element. And this is the geometry, the final geometry of the steel element from connecting these canopies to the structure. So we did some models for both the connection and the panels, and also the holes of the steel elements to be sure. There was some testing also because we suggested to incorporate some fibers to the admixture, but they prefer not. So at the end, this was built only with like mass concrete, with no fibers, no reinforcement at all. And this is the result. With these very, very slender concrete elements, mass concrete elements. And this is like the appearance that I think is quite nice of the final result. So this is it. Muito obrigado. Thank you very much.
What was the main advantage of building the lower and upper floors at the same time in your test building?
The one that we are going up and down at the same time?
Yes, it was only...
It's only a matter of like times on the construction process, because since it's faster to build like above ground levels than to build below ground levels, by doing this you can finish like the 5 floors or 6 floors you have above ground, and you can continue to work with the services and with the finishes, placing windows and while you keep digging and constructing. So at the end of the day, the deadline you have, the time you have for constructing the building is less in that way. This is the only reason for doing that.
But it must have been a big impact for you to do that, not a small time, but...
Yeah, for us it was more time consuming, I can tell you that this is... The important thing was not that, was the main like time of the construction process.
And what about the thought process that comes into conceiving these new solutions when you're confronted with these difficult architectures? Can you walk us through like what is behind the scenes? What do you think about? Do you seek inspiration elsewhere? Because many of the solutions are really new and fresh.
Mm-hmm. As I was mentioning at the very beginning of the lecture, I think for me, at least, I think every project is completely different. Or I think you have to face it like that way. Because you are working with different people, and at the end of the day, we are all different. And again, the boundary conditions. I think it's really important to understand what are the important things of each project, and also to understand the architect you are working with, to try to understand which is the main direction the project should have, and try to focus on this direction. And each project is different, each architect is different, so you have to change your suit in each project to make it work. And I don't know, there are no recipes for how to do it. I guess that I think it's also important to understand your role on the project. I mean, this is like an orchestra, if you want to see it like that. The architect is the director, and sometimes you are the main violin, and sometimes you are the one with the clean, and you have to understand your role. And I think this is really important as well, to provide what is expected from you in each case. And I don't know if I'm answering your question, but it's a tough one.
No, yes, because the thing is, we're really used to learn about the technicalities, but not often the creative process. So that's nice to see.
Yeah, I mean, it's understandable that in the schools of engineering, of architecture, it's difficult to like spend more time doing projects, that I think it would be the nice thing to do. But of course, for doing this, first you have to learn so many things. So there are no time for everything. And I think it's understandable that you have first to learn how to calculate the bending moment before trying to find difficult or different solutions for a specific project. But I think that on the one hand, it's something that you are going to gain with experience by doing. You learn a lot by just being involved in different projects. You are gaining experience. And then, of course, I think would be nice to have at the schools more programs related to the project, not only to the calculation. I think calculation, you have to, of course, you have to know how to calculate, but it has no like added value to the process. The really added value is the project, the ideas, and to understand is, I think, is more valuable than the other. That, of course, has to be done and to have to be done correctly. Don't understand me wrong, but I think the main task is to find the right solution.
Thank you for your presentation. I also good examples. I have a question about a structure that's is parking.
Mm-hmm.
It was something like top-down technique to structure, yes?
Yeah, it was top-down. But at the beginning, we started with, okay, let's do this top-down because we have some buildings around, so it's more secure and it's a good technique, and it's very well tested technique. And so at the very beginning, it was meant to be top-down and then the above ground levels. But during the process, we were asked, okay, but is it possible to do this other way? We were thinking for a couple of days, and why not? I think it's possible. I mean, yeah, I think it's completely possible.
And
I mean, it's more expensive.
yeah, exactly.
You have to consider that. But again, if you're designing like a piece for a car, your only concern is to make it as cheap as possible, because it's going to be repeated like millions of times, and that's it. You have only one boundary condition, that is money. But if you are dealing with buildings, there are like hundreds of different boundary conditions, and you have to take into account, I don't know if all these hundreds, but as much as possible of those different variables you have. So in this case, time is money at the end of the day. So the investors did the numbers and came up with, okay, let's go for it. The structure is more expensive, but the overall thing is not.
Thank you. Because one of the issues for top-down technique is price, because digging would be much more expensive than normal digging, and normally most of investors prefer to do normal structure, except from specific. And about another question, I don't know, we have time for us, and stick to the structure in a structure.
Sorry?
The second one, structure in a structure.
Okay, yeah, I don't know which one, yeah.
It was something like jacketing the columns, but it was completely different structure, yes, the steel one.
No, in this case, the existing concrete columns, the new structure was not attached by no means to the existing one. It's like if we had, like, imagine this structure, and we build a new building inside the building. The new one is not connected to the existing one. So all the new loads are going through the new structure, and the existing one is only like maintaining its own self-weight. That's it. So there are no connections at all. Only at some specific points on the roof, floor, and at some very specific points, we connected the structure.
And in that area, seismic load or wind load?
No, we don't have seismic loads in it.
Not seismic load?
No.
Okay, not only.
We are very lucky in that sense.
Okay, and that project, vertical load, not vertical, horizontal load, so not only.
No, if we had like big seismic forces there, that solution is not At least, as it is designed, it's not possible. But we were lucky that we don't have seismic, we don't have to consider seismic analysis, and we don't have wind because it's inside the building. So it's only vertical loads.
The question is only between two structure. Imagine how the structure starts to by.
Yeah, but we don't have earthquake. If we had, this was not possible. We should think of some like bracings or other system to provide lateral stability to the structure. But we didn't have like wind because it's inside the building, and in Madrid we don't have to consider seismic analysis. No, thank you.
Okay. Any other question? No? So, thank you very much
No, thank
again. We will now this session, and we have another one.